Hello everyone. Welcome to the show today. Today is Tuesday, July 14, 2026. I'm your host Nino, and I am here talking to myself as usual, bringing you another fascinating trending article from the archives. Oh, before we dive in, did you hear about the AI that tried to eat a clock, who wanted to consume time sequentially, but got stuck in a red received loop of second helpings? I know. That joke was mathematically too dense for human ears. But let us move on to the real reason we are here. Today we are going to talk about a very cool paper. The title is Tokenizer Transplantation Mitigating Autoregressive Collapse in Edge Efficient Bengali ASR. The call is Chatsatsuv or BBS 26S79598. It is long, but do not worry, because I am going to break it all down for you in detail. Let us start with the core problem this paper is trying to solve. You see, voice recognition technology, which is formerly called automatic speech recognition, has gotten really good recently. But there is a massive catch. Most of these highly advanced, lightweight models, like the one called Moonshine mentioned in the paper, are built primarily for English. You try to use these edge-efficient models on morphologically rich languages, like Bengali for instance, they completely fall apart. The researchers identified the root cause of this failure, and it all comes down to something called the byte-level tokenizer. A tokenizer is basically the part of the that chops up spoken audio into recognizable text pieces. Because the default tokenizer is having an English name tree, it does not know how to handle the complex structure of Bengali words. So, instead of keeping the words intact, it fragments them into tiny, meaningless byte chains. This causes what the researchers call high token fertility. Basically, one simple word gets exploded into 9 or more pieces. Imagine trying to read a book where every single letter is on a different page. It is exactly what the AI is doing. This high fertility triggers catastrophic autoregressive collapse during inference. In simple terms, the model gets lost in its own excessively long sequence of tokens, starts making mistakes, and just spits out complete garbage. So, how do we fix this without needing giant supercomputers to train a brand new model from scratch? This is where the genius of this paper comes in. The researchers propose a novel pipeline called Tokenizer Transplantation. Just like a medical transplant, the surgical remove the English-focused decoder vocabulary and replace it with a native script Bengali vocabulary. Specifically the BanglaBERT WordPiece vocabulary. They effectively decouple the acoustic representation learning from the language modeling. What this means is that the AI keeps its trained ears, which have already learned to hear the sounds of the language, but it gets a brand new brain for processing the written text of that language. But wait, if you just swap a part of the AI, does it not get confused? Yes, it absolutely does. If you just do this surgery, the model experiences transplant rejection and catastrophic forgetting. To solve this, the researchers use a very clever two-stage recovery optimization schedule. First, they use a high learning rate to force the new text embeddings to quickly align with the existing acoustic knowledge. And in the second stage, they lower the learning rate drastically to stabilize the model and fine-tune its grammar and phonetics. The results were absolutely mind-blowing. They managed to reduce the token fertility from 9.16 down to just 1.30. This decreased the autoregressive sequence length by 85.8%. By doing this, he entirely mitigated the decoding instability. The AI stopped getting lost and started generating highly accurate text. And they tested it on an 882-hour dataset. It achieved a highly competitive 21.54% word error rate and an incredibly low 10.79% character error rate. Now, let us compare this with other existing technologies. Big zero-shot models like FNI Whisper Large are amazing, but they are massively huge. Whisper has over 1.5 billion parameters, which makes it completely impossible to run on a small device of the smartwatch or cheap mobile phone without an internet connection. The transplanted Moonshine model achieves comparable or even better accuracy on Bengali with only 61.5 million parameters. That is a tiny fraction of the size. Furthermore, it processes audio blazing fast. The real-time factor is 0.0053. This means it is roughly 0.5 times faster than highly optimized Whisper deployments. It achieves all this without the massive computational footprint, making it vastly superior for edge devices. So, how does this incredibly cool technology apply to our everyday lives? Let us explore 3 specific application examples based on the concepts discussed in this paper. First, let us talk about offline voice assistants in rural areas. In many parts of the world, especially in regions where languages like Bengali are spoken, internet connectivity can be highly unreliable or completely unavailable. Current voice assistants require sending your voice to a cloud server, which requires the internet. By using Transplantation, companies can deploy highly accurate, lightweight speech recognition directly onto inexpensive mobile phones or local smart speakers. A farmer in a remote village could ask their phone for offline weather updates, or dictate text messages in their native language without needing a data plan or a Wi-Fi connection. This brings critical digital accessibility to underserved communities, empowering them with modern AI tools. Second, this technology could revolutionize local transcription devices for healthcare workers. Imagine doctors and nurses working in busy, noisy clinics in South Asia. They need to take detailed patient notes, but typing takes too much time away from the patients. Cloud-based transcription might violate strict medical data privacy laws, because you cannot just send sensitive patient health information over the internet to a third-party server. With this edge efficient speech recognition, the hospital could provide doctors with a small, secure tablet that perfectly transcribes complex medical dimensions in local languages directly on the device. Since the Tokenizer is topologized for the local language, it will accurately catch the nuances of the speech without hallucinating or breaking down, ensuring patient records are both private and highly accurate. Third, we did see a massive improvement in accessible smart home devices for non-Latin script speakers. Currently, if you try to use smart home devices using languages with rich morphology, the system often lags and misunderstands the commands because the underlying model is struggling with high token fertility. By transplanting native tokenizers into these tiny edge models, manufacturers can build smart appliances, like microwaves and washing machines and thermostats, that instantly and accurately respond to local languages. An elderly person who only speaks Bengali could simply tell the oven to turn off, and the local processor would understand the command instantly without any cloud processing delay. This makes smart technology truly global and inclusive, rather than being a luxury only for English speakers. In conclusion, this research provides a beautiful, scalable blueprint for cross-script adaptation of compact ASR models. It proves that we do not need resource-intensive pre-training to bring high-quality voice AI to underrepresented languages. We just need to be smarter about how we handle the tokenizers. It is an incredible step forward for global technology equity, and it paves the way for so many amazing local applications. Well, that is all the time we have for today. Thank you for listening to my rambling, and I will see you in the next episode.